This is a short recording of the FLUX model application for you to learn how to use FLUX 3.37 with the data that's been provided to you for assignment number 2 in BBE 4535 and BBE 5535. As you can see on the screen, I have the tabs for the FLUX model. I have 3.05 and 3.37. I'm going to open 3.37 by double clicking on it. You get this window, and then I select OK. It brings up this. With the this window, you can get started if you want to learn something about FLUX before you start working on it. There's a Help Me Getting Started tab. Also, anytime you're within the model, you can ask for help by going to the Help tab up here on the top. To get started then, with this window open, we go to Data. Used to be that FLUX, we're going to go to read. Used to be that FLUX would use what's called the using station index file, but that's really a throwback from the old DOS version of FLUX. And now we simply just need to use our data file, which in our case is in a Excel spreadsheet format. So we'll go to New Sample and Flow Data and New Stratification. It might be a little confusing when we talk about stratification, but this will bring us directly to getting our data file. Okay, bring up this window. There are two input files that are required: daily flow data and then sample flow data, or sample data, which has the chemistry as well as sample flow measurements. So you have two inputs, but all these inputs are in the single spreadsheet, so we're going to read that spreadsheet twice, one for the what we'll call the daily flow data and the other for the sample data. So we'll go to where that's located on the spreadsheet, or in my computer. And for this one, we have the file called Poplar, River, Flow, and TSS New. I have two different formats. One is old Excel, and then the other one is Excel 2010. We'll use the old one. I'm not sure what happens with the new one, whether or not FLUX will have a problem with that, but that's okay. You have the Excel for the old version of Excel, so it should work fine. So we'll read this one. We've selected it. And then it's going to ask me for a sample data file, which, like I say, is also in the same Excel file. So we're going to just read the same file again. Okay, so now it's reading that. Now it's going to bring up the files that it finds in the Excel spreadsheet. The first sheet that we're going to select is the continuous flow record 1912 to 2012. And for that, we're going to read, there's a couple headings. One is the date, the other is the flow. We're going to select the flow data. It's going to read, there's quite a few years of record here, so it's going to read 14,350. The record goes from 1912 to 1961, and then from 2002 through 2012. So it's a lot of data, and it takes a few minutes for it to read that. I guess it depends on how many pathways your computer has to get to the data as to how fast it will actually read it. Okay, Excel finally gets to this point, Flux finally gets to this point. We've read 14,350 observations. Took about 3 or 4 minutes for that to happen. And now it's going to ask for the next sheet. We have, we'll be reading in the sample data. There are 3 sample data sets according to the assignment. TSS and flow, and we have data from 2007 through 2012, 2002 through 2006, and 1984 to 2001. I'll select the one from 2002 to 2006. And when it asks, do we want to use the columns labeled, the site identifiers, you say yes, because then it'll ask for what data you want to read based on those identifiers. So the sample flow field, these are the flows that were measured when the samples were taken. And then the TSS is the flux constituent field. And we just go through and approve these things. We could modify the site name and all that, put in Poplar River TSS, let's say. And it brings up then this verification page, shows how much data there are, how many data values there are for both the flow and for the TSS. We can see for flow there's the within the samples there's 74 values, and TSS there's 74 values, and the continuous flow has 14,350 values. The means and the maximum values are given here as well for these variables. The flows are given in millions of millions of cubic meters of water per year. So there is a conversion that's done to go from CFS to million cubic meters per year. That conversion factor is 0.89373. So it's already said if our flow was in a different unit, let's say gallons per minute or cubic meters per second, we could use a different conversion factor. Concentration units are given in milligram per liter, so we're going to change from microgram to milligram per liter. And that conversion factor is 1,000. Okay, then we say done. Now we have this summary page, which shows all the information. We can see that in the samples, from the sample data, the mean flow was, which is only 74 values, 217.37 million cubic meters per year. The mean TSS is 24,333 microgram per liter, or 24.33 milligram per liter. The sample record is from 2002 to 2006. The flow record is from 1912 to 2012. We could shorten that up by doing a modification of the data. We can go to the Edit tab here, and we can select data to include or exclude. I won't do that right at this point. That's something that you can look at, so we could actually look, let's say, just at 2002 to 2006 for the continuous flow record. If we want to, we can do a quick plot. Or I might mention, I said something about the mean flow for the samples. Here's the mean flow for the continuous record. One might be suspicious as to whether the sample flow is representing the mean flow of the continuous record because of the big difference. If we were sampling over a much broader range of flows, we might come up with a more similar value to the one that's given for the mean flow. We might here do a quick plot, and you can see here discharge values. The green triangles are the discharges in million cubic meters per year, and the yellow triangles are the TSS in micrograms per liter. So you can see all the sampling is done in the, well, for this one, this sample set was 2002 to 2006. But we're using the entire flow record from 1912 through 2012. You can play around with that graph. There's options to modify the axes, the labels, or logarithm or non-logarithm, and so forth. Alright, very simple thing. We want to calculate the load, and we can do that here with the calculate command or the tab. We're going to compute loads. If I just click load, it's going to give me some values, and it's going to do that for all of the 6 methods. Well, it'll give 8 methods, but the 6 that we looked at. And it's using a single stratification, so all the flow data are calculated all together. And we can see here the flux in kilograms per year is has a broad range going from the method 1 through method 6. 6,884,000 kilogram per year for the average method. These other methods give numbers that are much more alike. An important thing here is the coefficient of variation. We can see that it's around 20%. And the idea, if you read the FLUX manual, it will explain that you should try to make it so that the coefficients of variation among the different methods is close. And also, if we use more stratification, or we would do that by using more stratification of the flows. And if we use more stratification, what we'd find is that the flux estimates would come closer to each other. Because theoretically, as you increase the stratification, the flux estimates should narrow down to where they're very similar, almost identical. So right now we have one stratum. All the flows are uniform. Close that, and what we'll do is we'll go up here and we'll go back to data, but now we're going to use the same data, but now we're going to stratify it. We're going to base it on discharge. So I'm going to immediately jump to 3 strata, and it tells you where the breakpoints of the strata are: 46, 187, 1493. It tells you how many samples are included within those strata. You need to have at least 4 values within each strata, or else you'll get an error. It doesn't like to work with small numbers of samples. So now we have the 3 strata. I can come back up here and do the calculation again. And you can see we have the 3 strata. This just summarizes for you the information about the strata. And if we come down here to the flux estimates, we see that the numbers are much closer to each other. All the coefficients of variations are very similar. So we're looking at a range among the different methods between about 2,338 metric tons per year and 2,738 metric tons per year. Metric ton is just this number divided by 1,000. The variances are given here. They look like really large numbers. The standard deviation would be the square root of those. Take the standard deviation divided by the mean, and it gives you the coefficient of variation. Some other things we can do here is to plot some things. So if we wanted to plot the exceedance curves, let's say time-based, which is what we did in assignment number 1, we get this kind of a plot. So we got discharge on a vertical axis and in a linear scale, and on the horizontal axis we have the percent of days at higher discharge. So it's similar to what, and that's actually on a log scale on the horizontal axis. So I could change that bottom axis to linear scale, and you can see that the graph starts to look similar to what we had in class. I'll change the left axis to a log scale. Alright, so that looks very similar to what we've had before. So the sample flow data are shown there. The daily flow data are shown there. They're different because the sample flow estimate of the flow duration is just an estimate of what the long-term continuous flow record is. And we also show the grab sample TSS values on here. So a graph like this can be saved and imported into a report. We can also we can look at the relationship between concentration and flow. See, in assignment number 1 you looked at this, and with method number 2 we've got 3 strata, so we've got 3 horizontal lines. Basically with method number 1 or method number 2 it's using an average concentration within each flow regime. So we got the 3 flow regimes here, and we can see that the we can see how the method is representing the concentration at a particular flow value in each of the regimes. So the regimes are listed by the different colors. You know, they go over different flow range. Those breaks in the line between the green, the blue, and the red were the breaks that were given when we selected the different strata. So the concentration that would be used for a given flow when there's no sample measured, there would be a concentration assigned to it, would be taken from these predictions or these representations. So if the flow is between about 180 million cubic meters per year and almost 700 million cubic meters per year on a particular day, the sample concentration that would be assigned to that would be the sample concentration associated with that red horizontal line. If we choose a different method, we just did the method number 2 there. If we choose method number 6 and do the plot, same type of plot, we see that we get, maybe we get a better representation. You can see there's quite a bit of scatter in the data, and you saw that in assignment number 1. But now, of course, in the higher flow range, we'd be using that red line to represent the variation of concentration as a function of the flow. And that relationship would be used for any flow that's being used to estimate load when there is no sample being given. You would predict that sample concentration from this relationship. Okay. And with that, I'll stop.